This is a problem from MIT Integration B 2026 finals. I think this is the fourth one of the tournament. Okay, now so we need to find this integral I, in which we have this integral from 0 to quarter, and we have a floor function, and inside that floor function we have 4th root of 1 by x minus 4, and we have a whole square here, and this is with power 1, no square here. So as we can see that x is from 0 to quarter, so I will use the identity. So x belongs to 0 to 1 by 4, so 1 by x will belong to 4 to infinity, and if I 1 by x belongs to 4 to infinity, then 1 by x minus 4 will be greater than 0, and hence 1 by x minus 4 to the power 1 by 4 will also be greater than 0. Cool. So now we have this, we have established that 1 by x minus 4, that is the inside term of this root, is greater than 0 for this range. So that is, it is defined just for the basic purpose. Okay, so now from there we can say that the floor function of this floor function is nothing but the greatest integer function. So this will be, if I call this floor function, value of this floor equals to n, so n will be a whole number, or let's say natural number including the 0. So what will the difference, like if we let's move on. Okay, you see now that for different x we can get different n, so that's why I've just given it delta xn. What is the difference between two consecutive terms in this function? Okay, now move on. Okay, so since I have established that that is, I have assumed this value as n, greatest integer of this value is n, so this whole will be between n to n plus 1. That is the definition of greatest integer function or floor function, that this value is between n to n plus 1, less than n plus 1 or greater than equals to 1. That's when this floor function is equals to n. So this is that. Now apply power 4 on all on each of the terms, so we'll get n to the power 4 less than equals to this, and less than n plus 1 to the power 4. Now add 4 on all of 3, so it will get to this, and after that you can see that after reciprocating it, why I'm reciprocating it, so that I can get the range on x. So I am reciprocating all the terms, and after reciprocating the equality, the sign will reverse. You know that I hope you know that if x is less than y, so if I write 1 by x, it will be greater than 1 by y. That's why I'm using it. So hence it will this will come to this, and this is the range of x. I have got a range of x in terms of n. After that, now I will move on to the integral part, that this is the original integral that I had assumed this value as n, so this becomes n square plus n, which is nothing but n into n plus 1. I can write it as n into n plus 1. Also I am converting this integral into summation. For that I will have to do that for this I will convert it into a summation varying on n. So see how I do it. So for converting to summation, you need to manage the integral. So for n is equals to 0 to infinity, the x will be from 0 to 1 by 4. You can put the value here from 0 to infinity, so x will be 0 to 1 by 4. And after that, for dx I will have to write a del x term. For dx, this was the original integral, and this becomes n into n plus 1, and this becomes summations n equal to 0 to infinity by the range that I have concluded, and this dx will be replaced by delta xn. So delta xn will be nothing but a difference of consecutive terms of this. So you can see that just put n is equals to n, and then put n is equals to n plus 1, and the difference of that will be the delta xn, difference of consecutive terms. That's it. Okay, now you contain n square common in the denominator. After that, so that it can be limited, it can neutralize this term, so I will take n square common, and that is the goal. After so this will convert to n into n plus 1 upon 4 plus n to the power 4 minus I am just separating the term first, this is the x and this is the separate, and then I will simplify it. So after separating it, this will become this and minus this, so we have two different sums. I will just simplify it separately. Now if I see this one, For n equals to 0, since we have n from 0 to infinity, for n equals to 0, this is nothing but 0, so I can take it from n equals to 1. So that's why I have taken it from n equals to 1, because 0 doesn't contribute anything. And after that, since I can write n plus 1 as n, substitution, I am using substitution. So if I write n plus 1 as n, this will reduce to n minus 1 into n upon 4 plus n to the power 4, and this will again go from 0 to infinity, because I have substituted n plus 1 with n. And you can just write it as t, n plus 1 as t, if you are getting confused, because this is a different variable, not this n, not cancel out this n, and this is different. Assume as a t, that would be more clear. So as I said, after replacing n plus 1 as n, this will reduce to this, and you can see that now I am combining both the terms, this term, the first term, and this simplified term. I am combining them. After why I am combining them? Because I have now made the denominator same. Now let's move on. I is equals to, so n into n plus 1 minus this n into n minus 1 upon 4 plus n to the power 4. Of course this n plus 1 will get to n, so I have written it wrong here, sorry about that. This will be n, so that's why the denominator is same, 4 plus n to the power 4. Fine. Now after combining it, you can see that the terms will cancel out here, so it will reduce to 2n, and in the denominator I have 4 plus n to the power 4. So this is the final summation that I have got. More simplified this is. Now write n plus 4 as n square plus 2n plus 2. I have written it here, yes, n square plus 2n plus 2 into n square minus 2n plus 2. You can just this is a standard if you are solving continuously this type of problems, but you can expand it and you will see that it will reduce to this. This is a standard result you can remember to simplify some of this type of problems. It is used quite a few times, that's why. Okay, now after this is reduced, this also can be written as, you can see this can be written as n plus 1 ka whole square plus 1, n minus 1 ka whole square plus 1. So that I have written it here. Now this denominator n 4 plus n to the power 4 is reduced to this summation, and this is the standard case of using the partial integration technique, where I divide it and try to cancel out some terms, the partial fraction technique. Yeah, now you can see this can be written as 1 upon n minus 1 ka whole square plus 1, and this 1 upon this, and it will get to 2. So I have divided by 2 in the here, this 1 by 2. That is that. Now move on. So next step, I have 1 by 2 here, and this is this. We will find the summation separately. Again we have here, I can replace n minus 1 by k, so it will go from k is equals to 0 to infinity, and this will become k square plus 1 after replacing k minus 1 with n minus 1 with k, and here I will replace n plus 1 with k. Of course both the k's are different, don't confuse it. You can use different variable if you are getting confused. So this again n plus 1 with k, so it will become from k is equal to 2 to infinity if I replace n plus 1 with k. I have written the substitution, you can write it, and if you are getting confused, you can write it as different variables k and something p. After that, this will reduce to 1 upon k square plus 1. This is 1 upon k square plus 1, and you can see that the limits are same, so only k is equals to 0 and k equal to term will remain. After that, from k equal to 2 to infinity, all of this will cancel out. So for k is equals to 0 and k is equals to 1 will remain. So it will become to half and 2. For k is equals to 0 it is 1, and k is equal to 1 it is half. So it will become half into 1 plus 1 by 2. It will reduce to 3 by 4. And hence this is the answer, a very sweet answer for a tough looking problem. Thank you.